بسم الله الرحمن الرحيم. Chapter 5, The Laws of Motion، يعني قوانين الحركة بالعربي. طيب, the concept of force. أول شيء, force can be defined as a push or a pull. That's a force. It's a push or a pull. And force is a vector, يعني it has a magnitude and a direction. Because it's a vector, we can apply everything we learned about vectors on the force. So, for example, we can add two vectors. This is vector 1, this is vector 2, and this is vector 3. It's the addition of vector 1 and vector 2. And we have subtraction, and all the operators work on the vectors will work on force. Here in this example, a very simple one, the force here is 1 unit and the force here is 2 units. Unit like 1 in Newton or 10 in Newton. The other one is 2 Newton or 20 Newton or 200 Newton. It depends. But the important thing in F2 is double F1. So two forces acting on this spring scale. The result is F, which is a vector, and we did that before when we sum two vectors. The amplitude of the force is F1 square, amplitude of force, magnitude of force 1 square plus magnitude of force 2 square under square root. And for the angle, you can use the cosine relation or sine relation or tan relation depending on the problem. برضو it's worth to note that in this chapter he didn't consider the angle with respect with 0 and going anti-clockwise. He just considered it as 26.6. And in the graph, you know that theta is in this area. تفضل عادل, تفضل.
Can you go back to the slide? Yeah. The vector 1u, isn't it supposed to be negative?
That's correct.
And thus we will have, I guess, another angle value. But you mentioned that we don't consider this chapter.
That's correct, yes.
So
it has a negative value, but it will not affect my answer at all.
All right, so if I would solve this problem, should I use absolute values or use the negative value, or depending on the direction?
Well, let me remind you, when you have an angle with a sine, you always look for the components to determine where is the angle. That's how we did it in the vectors.
Yeah.
So no matter if you have a sine or you don't have a sine in the angle, it will just tell you which quarter you are in.
Yeah, right.
And we said we solve this problem by looking at the components.
Okay.
He changed his method, by the way, and that's in my opinion, that's a weakness in the book, because if you assume a way of calculating the angle, you should stick to it, because it will be confusing. However,
this angle will have to be negative 26.6 because it's counterwise.
That's correct, but it won't matter in this problem.
Okay.
In this problem, it won't matter because already we know the angle.
Yeah, I got it, yeah.
If the angle is ambiguous, then you have to start from the positive x-axis and tell me if you need to add 90 or 180 or 270. But in this case, the angle is our least importance because we know what is the angle right away before we start even.
Okay.
Good?
Yeah, clear.
Yeah, we are not talking about the acceleration of gravity here, just the two forces. Just the two forces. طيب. So let's see first, before we start with Newton's laws, we need to understand, this is important, pay attention all of you. We need to understand the concept of inertial frame of reference. Inertial frame of reference. If the object does not interact with other objects, it is possible to identify a reference frame in which the object has zero acceleration. Zero acceleration. So you can determine your inertial frame of reference based on the fact that acceleration is zero. And it is very important when you want to solve problems of Newton laws that you determine where is your initial frame of reference. I have a 6 minutes video. I hope it will help you to understand it. So pay attention. Again, this is a very important concept. It will help you to understand the laws, the three laws of Newton. Resume. Start.
Hi, and welcome to High School Physics Explained. My name is Paul, and today I'm going to be talking about what frames of reference are, the two types, how you can tell the difference, and why an understanding of frames of reference is an important step in getting to understand Einstein's theory of relativity. So stay tuned. So what's a frame of reference? Well, consider it a bit like your own personal XYZ axis. It's the way you view the world, and everything around you is relative to you. So, relative to me, this ball is right beside me at a certain distance. So is the steering wheel. And around me, I can see cars moving, and I can see trees moving, all relative to me. Now, of course, that's relative to me and not necessarily to the people around me. But that's the point. Motion, its displacement, its velocity, and so forth, is all determined really by who is observing it. That's what we call it relativity. So as I drive around, everything is stationary. The laws of physics behave the way they should do. Everything around me is moving. So I'm stationary in my frame of reference, but the world around me is moving. But what about someone looking at me from the side of the road? If someone observing me going past, well, they would have a different perspective. They would see me moving and they're stationary, as opposed to them being moving and I'm stationary. So we're having different frames of reference here, and both are correct. So I've got this ball hanging here, and the reason I've got it hanging here is because it allows us to examine the laws of physics in terms of my frame of reference. Currently, it's hanging nice and vertically, and that's because gravity is pulling it down. Now, the fact is that I am stationary relative to you. The person on the side of the road would see me moving. So I actually am moving at the same time. Moving, stationary, it really depends on who's observing it. But the physics behind the motion of this ball doesn't change. So in reality, I'm actually not sure whether I actually truly am moving. Maybe the universe is rushing past me. Now I'm stationary now, and I always have been stationary relative to me, and the cars outside are moving relative to me. I'm in what we call an inertial frame of reference. the physics in this car is behaving like I expected to. So you can see this ball is hanging vertically as you would expect it to in a gravitational field. But in a moment, I'm going to accelerate as I go around the corner as the lights turn green. And let's see what happens to my ball. Swings back and swings to the side. In that case, I was in what we call a non-inertial frame of reference. That is, my ball is not behaving, and so as a result, you can tell that I'm moving. So an inertial frame of reference is a case where my frame of reference is moving at a constant velocity or it's stationary. Really what we're saying is there's no net forces being applied to my frame of reference. So I'm not accelerating, and that's a critical point. And as a result, the laws of physics behave as I expected to. And this is where the ball comes in. This ball is hanging down and as I would expect it to in terms of a gravitational field. Yes, it's swinging a little bit because of the bumpiness of the road, but it's not behaving counterintuitively. It's behaving as I expected. And you may have this happen yourself. If, for example, you were to stand on a train and it's moving at a constant velocity, you could throw the ball up and down with relative ease. It behaves just as if you're stationary. But that's the point. You're stationary relative to you. You're not stationary relative to the person on the platform. And so the laws of physics behave as you would expect them. But what if we added acceleration to our frame of reference? I'm now about to go into a roundabout. So what you notice now is that the ball swung out. It did not behave in terms of my gravitational field. There's other forces at play. It's non-inertial, and that's why we call it a non-inertial frame of reference. And only then do I know I'm actually moving because I'm non-inertial. So I'm back now in my inertial frame of reference. Inertial because my car is now going at a constant velocity. But the fact is, I'm actually still stationary relative to me. I'm only moving because the trees around me appear to be moving, but for all intents and purposes, I'm actually still stationary, and someone's got a computer screen playing a moving picture. And here's the rub. I can't prove that I'm moving, because in fact, it all depends on who's observing that will determine whether I'm moving. And so therefore, there's no experiment that I can do that proves definitively that I'm moving.
Well, if it is a new concept for you, uh, from the first time you will not get it, because inertial frame of reference depends on assuming that the frame of reference that you are in and you need to apply the laws of physics to it, you need to have a constant velocity, يعني acceleration must be equal to 0. If you have any kind of acceleration, then the inertial frame of reference, you cannot apply the laws of physics as we know them, the Newton's laws of physics, if you don't have an inertial frame of reference. يعني if you go into acceleration, if your frame of reference has any acceleration, then you cannot apply the laws of Newton laws to it. You must have the condition that your frame of reference acceleration is equal to 0. You can go with a constant velocity, yes, it will apply. It is considered an inertial frame of reference. That's what he was talking about. That's the first point. The second point, he said, well, if that is the case, then I cannot do any experiment to prove that I am moving, because I cannot moving with a constant velocity, because I cannot determine if I am moving with a constant velocity, that I am moving in a constant velocity. It could be I'm stationary and everything around me is moving. So if I want to know if I'm moving in a constant velocity, the observer has to be from outside my inertial frame of reference. Other than that, I cannot know. That's what he was trying to say. So in order to apply Newton's laws, you need your inertial frame of reference must have zero acceleration. Constant velocity, no problem. Any acceleration, it will affect the laws. وضرب مثال هو بالقطار. احنا نضرب مثال بالطيارة. الطيارة أسرع من القطار. الطيارة تكون سرعتها 900 كيلو في الساعة. وstill inside the airplane you are stationary. And you will not know that the airplane is moving unless you look outside and you compare your frame of reference to the outside frame of reference. Then you will know the airplane is moving. That's what he was trying to say. I suggest for you see the video once, twice, 3 times in order to grasp the concept. Constant acceleration, we cannot notice any change. لا, constant velocity. Constant acceleration, of course, you will realize the change. When he has the ball hanged from the ceiling and he accelerated his car, right away he knew that he is moving because the car moved backward. So if there is acceleration, you know. But if there is zero acceleration, if you are stationary or going with a constant velocity, you cannot know that you are moving unless you compare with an observer outside your inertial frame of reference. Net force must be equal to 0 on your frame of reference. طيب خلينا نكمل. Once we understand a frame of reference, inertial frame of reference, now we start talking about the laws of Newton. طيب, the first law. In the absence of external forces, and when we viewed from an inertial reference of frame or frame of reference, يعني acceleration is equal 0. On an object at rest, an object at rest remains at rest, and an object in motion continues in motion with a constant velocity. هذا القانون الأول. إذا بتتذكروا حفظونا إياه في العلوم، الجسم الساكن يبقى ساكن والجسم المتحرك يبقى متحرك في خط مستقيم ما لم تؤثر عليه قوة خارجية تغير من حالته. تذكروا حفظونا إياه يعني زي القرآن قد ما حفظونا إياه. هذا القانون الأول. القانون الأول to be effective you need to have inertial reference frame or inertial frame of reference. Then if your frame of reference has 0 acceleration, then the object in that frame of reference, if it is stationary, it will stay stationary forever. If it is moving, it will stay moving in a constant velocity forever in that frame of reference. The condition in the summation of forces on the frame of reference, inertial frame of reference must be equal to 0. هذا القانون الأول. This is the first law. طيب, now we come to, Doctor, I didn't get what the law means. First of all, let me repeat. First of all, in order for the first law to work, first law of Newton to work, you need inertial frame of reference. What is the meaning of that? That means your frame of reference acceleration must be equal to 0. You don't have any acceleration in your frame of reference. Is that clear, Yusuf? That's it. So if you have an inertial frame of reference, then in that inertial frame of reference, if you have an object that is not moving, it will stay stationary forever. It will not move if there is no force acting on it. And if that object is moving with a constant velocity, it will stay moving forever at that constant velocity unless an external force acts on it. That is the first law of Newton. ممتاز وشكرا على السؤال. طيب هلا to talk about Newton's second law, we need to identify the mass. What do we mean when we say mass? And this is one of the concepts that people mix it in real life. اللي هو mass and weight. Mass and weight. People in real life, يعني if you want to ask a person what is his mass, in real life, what do you say? You say, what's your weight? And they are completely two different quantities. We have the weight, which is a force, and we have the mass, which is kilogram, So mass is a property that specifies how much resistance an object exhibits to change in its velocity, اللي هو الانيرشيا اللي هو عرفناها الانيرشيا أو resistance of change, its status. If it is stationary, it will resist to move. If it is moving in a constant velocity, it will resist to stop. That's the inertia. That's the mass. The definition of mass. طيب والweight? الweight, it's a force caused by the attraction between two masses. الفورس, gravitational force أو الweight, it's a result of the attraction between two masses, and it's just a force. Mass is constant if it is on Earth or if it is on the moon. However, weight on Earth is much larger than weight on the moon for the same object. طيب, let's skip هاي لأنه very clear. Now we come to the second law of Newton. Again, look, when you viewed from an inertial reference frame, again, it's inertial. يعني your frame of reference acceleration must be equal to 0. You are allowed to accelerate within your frame of reference, no problem, but the frame of reference has 0 acceleration. Then if you have frame of reference 0 acceleration, you can apply a Newton second law اللي هو في هاي الصيغة إنه summation of forces as vectors, as summation of vectors is equal the mass, and not the weight, the mass multiplied by the acceleration. Or as he wrote it, more meaningful like this, إنه if you apply a net force on a mass, you will create acceleration. This is more meaningful than the one we use, F is equal ma. No. If you apply a net force on a mass, you will cause the mass to accelerate. You will cause the mass to accelerate, and we write it like this. What's the meaning of that? That means it will apply in the x-axis, the y-axis, and the z-axis. So in the z-axis, summation of forces in the z-axis is equal the mass multiplied by the acceleration in the z-axis, for example, and then the y and the x. Units of force, it's in Newton. And what is Newton? Well, M is kilogram, A is meter per second, so it's 1 kilogram meter per second. That's the unit of force. طيب الحين خلينا نيجي على concept اللي هو الجرافيتيشنال فورس والويت زي ما حكينا. هلا we know that F is equal ma, that's a general law if we have an inertial frame of reference. يعني our frame of reference is not accelerating, then we can apply Newton's second law, which can be applied on gravitational force because it is a force, and the magnitude of that force, we call it the weight, is equal mg. The magnitude, يعني the weight, is equal mg. So basically we call this is the weight. This is the weight. And from where we have the weight? From Newton's second law, F is equal ma. طيب الحين pay attention إنه G is not constant on Earth. G varies within a geographical location. G is not constant on Earth. In most places it's 9.80 or 9.81. However, on a very high altitude building, gravitational will be a little bit weaker, and then the weight on the ground is more than the weight at the top of that building. And also, for example, if you are on a mountain, your weight will be a little bit less because gravitational force is weaker. طيب, what is the cause of that? We know that the force between masses is just a constant, and then we have the mass of the planet and the mass of the object divided by r square, and that is equal to F is equal ma. So m, let me change the color, equal to mg, because this is a force and is equal to mg. This law is the law of gravitation between two masses. This law is the source of gravitational force. It's attraction between two masses. We have a constant, the mass of the big planet, and the small mass of the object divided by r square. So m will go with m. So we end up that G is equal that constant multiplied by the mass of the planet divided by r square. And this is to show you that gravitational acceleration I will talk about r. Gravitational acceleration depends on r square. R is the distance between the two objects, but it's the distance between center of masses. Yaman, ahsant. You have a good grasp of physics principles. It is not the distance between the Earth's surface and the object. No, it is the distance between center of masses of both the planet and the object. So as you can see, when r square is larger, gravitational force is smaller. And they calculate it, they measure it. For example, at a mountain, G can reach 9.77 meter per second square. And top of a mountain مثلا. Similarly, when you go into an airplane, and the airplane is 11 kilometer above the ground or 12 kilometer above the ground, your weight become less. طبعا how much less؟ يعني approximately 0.1 Newton or 0.2 Newton. That's it. For a person who is 100 kilogram, when you go about 10 kilometers, maybe it will be around 1 Newton. So he is 1000 Newton. So on the airplane, he may reach roughly 999 Newton. So that's a concept we need to understand. You need a diet, just go up a mountain and weigh yourself. Yep. So that's because يعني انتو باعتبار انه that's a course for engineers, you need to understand that G is not constant everywhere. You need to understand that. Even at different areas on Earth, you may have different acceleration. طيب. الحين let's talk about what they say, a silly mistake that they did when they sent the astronauts to their first journey. They did a silly mistake. What is the mistake? What is the mistake? First of all, we know that F is equal ma. So they calculate, they said this suit for the astronaut weighs on Earth 136 kilogram. They can't send light clothes يا شيخ لأنه في radiation وفي حرارة منخفضة جدا. It has to be thick. هلا breathing apparatus هذا breathing apparatus the weight on Earth is 136 kilogram. So they said, okay, we do our calculation that the astronaut, when he is at the moon, he will feel like it is about 23 or 22 kilogram. طيب, how did we calculate that? The weight, we said mg, and on the moon 136 kilogram multiplied by 1.6 meter per second square. So it will be what? 217.6 Newton. And what is that equivalent in weight? Well, on Earth, equivalent mass اللي هو force divided by 9.8 يعني 217.6 Newton divided by 9.8, it will be like 22 kilogram. So they said, okay, for the astronaut, it is okay to carry a 22 kilogram because that's what he will feel on the moon. Now, what is the mistake, the silly mistake that did? They account for the gravitational mass. Yeah, that's the gravitational mass. This is the gravitational, due to gravitation. But there is another mass اللي هي inertial mass. Inertial mass اللي هو because of the mass of the object, it will affect the motion because at the end of the day, F is equal ma. So gravitational mass is that the direction of the vector of that, it's like this. It's not showing. Gravitational, it's like this. That's gravitational mass. Inertial mass, well, if the astronaut want to move front or to the back, to the left, to the right, he will need to put a lot of force because at the end of the day, still F is equal ma. And we didn't decrease the mass of the one that he is carrying at his back in terms of horizontal motion. So it was difficult for the astronauts to move horizontally because of that concept. شكلهم هدول they didn't take 101 physics ولا 191 physics. They didn't take it or they took a bad mark in it. طيب هلا third law of physics, if two objects interact, inertial mass اللي هو if they want to move, يعني if you want to move horizontally, still F is equal ma on the moon is equal F is equal ma on Earth. It will not change horizontally. Vertically, yes, it's less on the moon, but horizontally, it's the same. Yeah, the astronaut weight will be less, but if you want to move horizontally, it will be the same effort he want to do like on Earth, horizontally. To be less too, so the ratio between the weight is the same. That's what I mean. لا, I mean إنه if you talk about the weight اللي هو vertical force on the moon will be less than Earth. But if you talk about the horizontal force that need, if you want to move, you need to apply a force horizontally. That horizontal force on the moon and on Earth are the same. Horizontal force are the same because F is equal ma. Nothing change. Okay. طيب, if two objects interact, yeah, X component will not be affected if you are on the moon or in space. حتى لو يعني net force of gravitation net force applied on the object are 0, still in the x-axis you will have the same, you have the inertia of the mass. You have the inertia of the mass. Bullet on the moon, it will just cover more distance. لأنه gravitational is weak. فهو horizontal component will be the same. The vertical component will be weaker. Gravitational will be weaker. So the bullet will go, will take more time when it goes down. That means it will cover more horizontal range. That's correct. That if you fire your bullet horizontally, if you fire it as a projectile, it will also cover more vertical range if you throw it as a projectile. But if you fire your bullet horizontally, it will just cover a more horizontal range. If two objects interact, the force F12, that means the force exerted by object 1 on object 2. Now, please memorize this. Now, pay attention, memorize it, لأنه it will be confusing in the coming slides. What's the meaning of F12? So I have object, that is 1, and I have an object that is 2. So F12, the force applied by object 1 on object 2. That's the meaning. طيب, what is force 2-1? اللي هي the force exerted by object 2 on object 1. When we deal with vectors, F12 is equal minus F21. Same magnitude, opposite direction. طيب, here we have 1, 2, that means the force applied by object 1 on object 2. F21, يعني object applied from object 2 on object 1 وفي minus sign اللي هو in opposite direction. طيب, what is FG اللي هو الweight? الweight is the force applied by Earth on a projectile. If it is a free fall or projectile motion in 2 dimensions, that means that's the force of Earth on the projectile. And FPE is the force of the projectile on Earth, and it's equal the minus the vector. Minus the vector. No, every action has an equal and opposite reaction. Every action has an equal and opposite reaction. يعني if Earth pulls an object, the object pulls Earth. Same magnitude, opposite direction. يعني if a stone or an object is falling down, Earth is pulling the object downward, the object is pulling Earth upward while he is falling. F is equal ma. That's correct. How? That's the nature of things. Every action has an equal opposite reaction. That's the nature of things. If when Earth is pulling, يعني for example, airplane flying at 10 kilometer height. So air is pulling the earth is pulling the airplane downward, and the plane is pulling the earth upward. Same amount of force, opposite direction. Every action has an equal opposite reaction. Of course, all of us, if earth is pulling us, we are pulling earth. But لاحظ, when you compare the masses, same force, F is equal MA. تمام? For the object, and this is equal, F is equal M the planet multiplied by A the planet. Not P, let's use Earth. Yeah, so same force, but because Earth mass is a humongous, then the acceleration will be tiny that we cannot even measure with our equipment. We cannot even measure with our equipment. So Earth is pulling you, you are pulling Earth. Same amount of force, opposite direction. طيب, let's see this confusing picture. First of all, this is a monitor. This is a monitor. The monitor has a gravitational force, Fg, which is equal the force of Earth acting on the modem, on the monitor. That is Fg. That is the action force. As a result, there is a reaction force. We call it F, monitor on Earth, same magnitude, opposite direction. Clear? طيب. Now let's look at this pair. Well, we said that there is a gravitational force, Fg, and now he called the force F monitor on the table. It is the force of monitor on the table due to gravitational force. And as a result, there will be a reaction force from the table on the monitor. So here, monitor, table, here, table, monitor. And here, he is just rewriting this, separating it from the other two forces. I'm repeating, Fg is equal the force of Earth on the monitor, والnormal force اللي هي the force of the table on the monitor. Action and reaction. هلا pay attention إنه الأكشن and reaction pair cannot be applied on the same object. Action in one object, reaction on the second object. يعني for example, I have a box, a red box, and in top of that red box I have a blue box. And that space is just left like this just for illustration. They will be on top of each other. Type. What is the action force? Mg. That is M. طيب. What is the reaction force? اللي هي normal force is equal minus mg. تمام؟ فلاحظوا إنه الأكشن فورس from the blue object on the red object happen on the red object. Reaction force happen on the blue object. You cannot have both in the same object. Action and reaction, one in one object, the other one in the other object. That's important concept. Now we will answer your question, Yusuf. طيب. هلا because the object or the monitor or whatever, when it is stationary, that means it's not moving, then summation of forces must equal to 0. And what are the forces? Well, we have the mg force and we have the normal force. We call it normal, that means perpendicular. Normal مش إنه طبيعي، ما بتترجم طبيعي. Normal means perpendicular to the surface. عشان هيك نحكي لها normal force. It is perpendicular to the surface. So normal force is a vector and gravitational force is a vector. And because the object is not moving, that means must equal to 0. There is no acceleration and the object is stationary. طيب, let me remind you, when we say summation of forces equal 0, that means summation of forces in the x-axis must equal to 0 and summation of forces in the y-axis must equal to 0. So we write the components and now the minus sign appear. So n in the j direction, unit vector j, minus mg in j, because it's pointing down, is equal 0. That means n is equal mg. N is equal mg. The magnitude, أحسنت. If you want to talk about vectors, n is equal minus mg. That is if you are talking about vectors. But in magnitude, n is equal mg. 10 Newton, 10 Newton. That's the magnitude. Vector minus 10 Newton downward plus 10 Newton upward. Clear? That's a confusing one. But again, if you talk about vectors, yes, you have a minus sign. If you talk about magnitude, the minus sign disappears because as we derive it here. طيب. الحين let us introduce you to 3 diagrams. This one, so many vectors, we call it forces on the objects to illustrate everything in the graph. And this one, we call it force diagram for one object. And this one, and this is important, I saw so many Physics 1 exams. In the problem, he will ask you to draw the free body diagram. We call it free body diagram. Free body diagram. طيب شو هذا الفري body diagram? First of all, our object, it's a dot at the center of mass of the object. So it's a tree, it's a car, it's a stone, it's a ball, whatever. We just put at the center of mass as a dot, and then we draw the figures, the vectors of force. We draw the vectors acting on the object of force. This one, forces on the object, يعني spaghetti. You cannot solve a problem using this this one. It's confusing, very confusing. So when you solve a problem, we use a free body diagram. And as I told you, I saw many questions. The first question, they will tell you, draw the free body diagram. FTM. FTM اللي هي table monitor. FTM table monitor اللي هي reaction force. وال EM اللي هو earth monitor. وال EM يعني earth monitor. النورمال فورس اللي لانه جايه من every action has an equal opposite reaction. The monitor is putting action force on the table. The table is returning back the force in opposite direction, same magnitude, to the book or to the monitor. اي نعم، زي ما قلت لكم انه يعني كثير اسئله اول شيء بيحكي draw the free body diagram. The action, you mean the action and reaction? Action and reaction. Of course, action and reaction, if you sum them as a vector, it will become a zero. We have a static equilibrium يعني. If you add the forces as a vectors, it will give you a zero. طيب. ما بعرف عاد يكفي الوقت ولا لا. Let's see. طيب هلا when we try to solve a problem, let's finish this and then you can go and enjoy the holiday. When we try to solve a problem using Newton's second law, we need to look at those advices. Two analysis model for solving problems. Objects in equilibrium اللي هو acceleration must equal to 0, or acceleration under action of constant external force. And here let's pay attention, it is external force and it is constant. So when we solve, وإن شاء الله هناخد several examples إن شاء الله. When we solve Newton's second law, we have two situations. The first situation, either acceleration is equal 0 or acceleration under action of a constant external force. يعني either A is equal 0 or A is equal constant. هاي الحالتين اللي احنا حنتعامل معاها بقوانين نيوتن الثانية. هلا remember, interested only in external forces that act on an object. So if objects modeled as particles, no need to worry about rotational motion such as spinning. We just, it's a dot. It's the center mass of the object. And for now, neglect friction. طبعا كمان شوي على آخر الفصل هندخل بالفريكشن وبصير you cannot ignore friction. طيب. Usually neglect mass of any ropes, strings or cables involved. هاي كلها ايش؟ We ignore the mass of it. It will not affect our calculation. Assume magnitude of force exerted by any element of rope on adjacent element, same for all elements along the rope. انه بنعتبر الروب مثلا نعتبره identical، معناته الفورس موزعة بشكل متساوي. Words like light، يعني يمكن see a light rope معناته neglect the mass، or neglect the mass of the rope. Also you neglect the mass of the rope. So that's you take into consideration. When rope attached to object pulls on an object, rope exerts force on an object in a direction away from the object parallel to rope اللي هو magnitude T of the force اللي هو is equal tension in rope is a scalar quantity. Scalar quantity. What's the meaning of that? يعني let's give a small example, very fast one. So this is mass, and here we have a pulley. And here we have another mass. Let's say this is capital mass and this is small mass. So here we have tension. Same scalar quantity, tension. It's pulling up and we can consider it here tension. It's pulling this way. Yeah? So don't be confused because when we solve the problems, magnitude T of that force, the tension in the rope, it's a scalar quantity. So صحيح هون tension is pulling up, but when we look at the tension here in the mass, it is pulling right from left to right. So don't be confused with that. We will solve so many inshallah questions how to calculate the tension. So let us stop here and we will continue inshallah on Wednesday. Wednesday, correct? Yes. Let me stop recording.